AI is not waiting for more math engines. It is waiting for the pieces that keep those engines fed. The headline answer is HBM memory and the advanced packaging that binds it to a GPU. But that is only half the story. In the US-China contest, the deepest choke point sits earlier, the equipment and know-how that make leading chips possible. People call every expensive AI chip a GPU. That hides the real supply chain. A CPU runs the operating system. A GPU is the flexible parallel workhorse. A TPU is a purpose-built AI accelerator. And memory is the warehouse beside every one of them. The scarce thing is often not the silicon brain. It is the path between the brain and its data. Here is the verdict. In the commercial AI boom, HBM and advanced packaging are the tightest near-term gates. GPUs are constrained partly because of them. TPUs and other custom chips are squeezed by the same shared inputs. CPUs are important, but they are not the queue holding up the AI build-out. Then geopolitics changes the map. Tools, design software, and advanced node manufacturing become the strategic gate. Start with the component doing the quietest and most important work. Ordinary DRAM is the general-purpose working memory in laptops and servers. HBM, or high-bandwidth memory, is different. It stacks DRAM dies vertically and puts that stack extremely close to an AI accelerator. That short path moves far more data per second. It is not a nicer version of laptop RAM. It is a different physical answer to an AI problem. Why does that matter? Modern AI is constantly moving model weights and intermediate results. If arithmetic units wait for memory, adding more arithmetic units does not solve the delay. That is the memory wall. Compute can exist on paper, but useful throughput stalls when data cannot arrive fast enough. HBM attacks the wall with bandwidth, density, and proximity. The physical scale is easy to miss. A memory die can look tiny in a technician's hand, yet every stack must be made, tested, connected, and cooled reliably. That is why this market is not just about adding DRAM wafer starts. It is a difficult stacking and yield business. Demand has changed the economics of memory. AI systems prioritize high-bandwidth stacks, while suppliers have to qualify new generations with exacting customers. Micron's latest materials point to continued HBM development, including HBM4E volume production expected in calendar 2027. The honest takeaway is not that every memory chip is equally scarce. It is that premium AI memory is its own tight market. But memory alone does not make an AI accelerator shippable. A GPU is thousands of smaller compute lanes built for parallel work, graphics, simulations, and the matrix calculations behind neural networks. It is flexible, and NVIDIA's software ecosystem made it the default tool for much of AI. But a high-end GPU is no longer just a logic die. It is a system assembled around giant amounts of nearby HBM. That assembly is the advanced packaging problem. Technologies such as TSMC's CoWoS place the logic and HBM together on advanced packaging. Think of it as the high-speed neighborhood that lets the accelerator talk to memory. If the factory can print a GPU die but cannot package the complete module, customers still do not receive an AI server. This is why the popular line that foundries can simply print more GPUs misses the bottleneck. Leading foundries must allocate advanced node wafers, packaging capacity, substrates, test capacity, and HBM supply together. A shortage at any one of those points becomes a shortage of the finished accelerator. So is the GPU a bottleneck? Yes, from the buyer's viewpoint. But the useful diagnosis is more precise. GPU availability is entangled with HBM and advanced packaging. That matters because building more compute cores alone does not clear the queue. The supply chain needs a balanced increase in all three pieces. Now separate flexible AI compute from specialized AI compute. A TPU, or more broadly a custom AI ASIC, trades flexibility for focus. Google's Trillium TPU is one example. Google documents 32 gigabytes of HBM per chip and says Trillium doubled HBM capacity and bandwidth over its earlier V5e generation. Custom silicon can be very efficient when its software and workload fit. It is not a magic escape from memory. That is the key supply insight. Custom chips can reduce dependence on a particular GPU vendor and a particular software stack. They do not remove dependence on advanced foundry work, advanced packaging, and high-bandwidth memory. In a tight market, TPUs, Trainium-style chips, and other ASICs compete for overlapping parts of the same industrial pipeline. CPUs are different again. They handle sequential work, operating systems, networking, storage control, and orchestration around accelerators. Every AI cluster still needs them, but CPUs do not usually require the same giant HBM plus advanced package configuration as a flagship AI accelerator. That makes their supply picture much less acute than the AI memory lane. Put the four together. HBM is the critical commercial bottleneck. GPUs are highly constrained finished systems because they need HBM and packaging. TPUs and ASICs are a growing alternative, but they inherit much of the same physical constraint. CPUs are the steady coordinator, strategically important, but not the main reason an AI cluster waits. Then the supply question turns into a strategic contest. The commercial question is, what slows an AI cluster from shipping this quarter? The chip war question is, what prevents a country from building or scaling the whole leading-edge stack over years? Here, the answer is not simply a GPU ban. The crucial layers include semiconductor manufacturing equipment, electronic design tools, advanced node process knowledge, HBM, and packaging capability. U.S. export controls reflect that stack. BIS materials describe controls on advanced computing chips, advanced node chip development tools, and high-bandwidth memory. In 2026, the policy also changed in one direction. Certain H200 and comparable products can be considered case by case for approved Chinese customers. The rulebook is active and specific. It is not a simple permanent off switch. One correction matters. EUV lithography is a powerful leading-edge tool and an enormous strategic advantage. But saying it is required for every 7-nanometer chip is too simple. China's SMIC has demonstrated 7-nanometer class production using older DUV techniques at a cost in complexity, capacity, and yield. The bottleneck is not a magical single machine. It is the ability to produce leading chips repeatedly and economically. That gives each chip type a different strategic profile. Advanced AI GPUs are hard because the hardware and software ecosystem matter together. HBM is hard because high-end, stacked memory needs deep process and packaging expertise. Advanced CPUs and AI ASICs need leading logic manufacturing. NAND storage is comparatively closer to parity than cutting-edge AI memory, but that does not erase the leading-edge gap. So which chip is the bottleneck? It depends on the clock you are using. For the next AI server, follow HBM and advanced packaging. They are the closest thing to the current commercial choke point because a finished accelerator needs both. For the long geopolitical race, follow the full tool chain: lithography, etch, deposition, metrology, design software, advanced node manufacturing, memory, and packaging. That is the layer where dependence becomes strategic leverage. Watch 3 signals. First, whether memory suppliers can qualify and ramp new HBM generations without giving up yield. Second, whether advanced packaging expands at the same pace as accelerator demand. Third, whether China can turn demonstrations into high-volume, economical production while controls keep shifting. Those signals tell you more than a single GPU launch headline. The AI boom did not run out of chip designs. It ran into the physical reality of moving data, stacking memory, packaging systems, and controlling the tools behind the tools. That is where the leverage is. Follow Mankey markets for the next map of the AI supply chain.